recording. But doesn't mind, it's just Wiederholung. We repeat that stuff. But shifting this channel doesn't mean that you generally increase the current. It is in the first approximation, the current stays constant. You have a resistor. And the amount of electrons which is available is fixed by the gate source voltage, and this amount of the electrons, the density generates a drift current through the space charge region. Yeah, so here we are at a constant current at the first approximation, and the constant current increases by increased gate voltages. Let's try. It's now my purpose is not the calculation itself. My purpose is the path we go through to calculate this current. Okay, so we try to understand how we have to treat all these equations to get a drain current as a function of the drain source voltage and the gate source voltage. Okay, now let's start. So we are in the linear region, so the channel, one moment. Okay, so we are in the linear region. A linear region means we have a complete channel. What does that mean for the potential within the bulk? The potential changes, and the gate bulk potential is as a function of the location. Well, we know all that, but now we have the equation for that. The gate bulk voltage is here, the gate source voltage. The gate bulk voltage is the difference between gate source and the Vx. Okay, this is placed here as an equation. So we'll have a location dependence. Let's go on. We go on with the inversion charge. We know that the inversion charge is a function of the gate silicon, so metal oxide semiconductor. It's a function of the voltage here. We know that. And this voltage is a function of the location. We know that now also. And therefore, we simplify that the change in the charge is a function of the change in the voltage. And the next approximation, but this is also not new, the charge in the inversion layer is zero if we have the threshold voltage applied to that location. Yes, that's also not new. Let's put there the page number where we have stated this the first time. We said that first here. We said that the inversion charge is zero by the voltage defined as 2 VIF as at the surface plus oxide. So that threshold. Okay, so page 81, I wanted to place the page number there. 1 second, please. So we say page 81. Let's continue. So as we have a location-dependent voltage, and as the charge is a function of the voltage, we have a location-dependent charge. Well, how we calculate the location-dependent charge? By, okay, the sheet capacitance is constant because we assume that the geometries are constant, not as a function of the location. And what is the charging voltage? It's the overdrive voltage, okay? And the overdrive is VGS minus V threshold in general, but the VGS is not VGS, it is VG bulk. And gate bulk is location dependent. And do you know what the second complication is within this equation? We are not only location dependent, the threshold voltage itself is voltage dependent. You know, if you change this potential here, you change the threshold voltage because this voltage you have to apply changes if this potential changes. Therefore, your threshold voltage itself is voltage dependent and therefore also location dependent. So we put all these dependencies together here. So we have a gate source minus location voltage and the threshold voltage, which is again a function of the voltage. Well, and if we put together and mix and pour out, we get a threshold voltage, which is a function of the location, and a threshold voltage where we have under the square root this voltage as a function of the location. Why? This is not affected because this one is the definition. And yeah, and this one is changing your defined potential. And this change you have to compensate for. And therefore, the threshold voltage is at the end location dependent. Okay, so we have something. My aim is that you understand the following thing. Your gate bulk voltage is a function of X. Therefore, Q is a function of X. And therefore, the threshold voltage is a function of the location. Okay, go on. Now we want to understand how we get the current. For the current, we need the charge. Okay, we have it. With the charge needs to be transported. How? By applying an electric field. Who is applying the electric field? You are applying the electric field by applying a voltage. Okay, but the movement, the velocity, is also a function of the location. Because you have an electric field, which is also a function of the location, and times mobility. Okay, at the moment, the mobility, we assume the mobility, up to now, we have assumed the mobility is given by the location, by a semiconductor. But this semiconductor ends up here. So our assumption of a perfect crystal is not valid because it stops there. Here you have a silicon uh, oxide. And here you have the perfect silicon with its covalent bonds. And here the bonds are ending to, let's say, oxide, O2. Assume here two oxygen atoms. Therefore, the mobility at their interface is not the one you have in the bulk. And for the sake of the simplicity, you say that your mobility in the MOSFET, in the channel, is just half the mobility in the bulk. Okay, now we have that part. Let's continue. We require for the drain current the carrier density, the velocity. And we have to say that the current itself is defined by the width. So we know how wide the transistor is. We know the area where the current does flow. We have the amount of charge, and we have the velocity of this charge throughout the width. Okay. Now we put in these equations we have acquired up to now. The charge we have here. The velocity we have here. And the electric field we have here. And we put in the electrical field, the velocity here in, the charge here in, and we get this equation. What do we see? We see that the electrical current is location dependent, and the location is in the charge and in this location dependent voltage. Okay, but do you know that the current is constant all over the location? Because nowhere the current is disappearing. If you put in here 10 amperes, you pull out 10 amperes. So if you assume that all geometries are perfect, then at all location the current is constant. And if we do know that, we can say, one moment, one moment. I can say, I take these changes towards this way. So the change of the current as a function of the location is equal to the change of the voltage. So the change of the current as a function of the voltage location is the change in voltage as a function of the location. But at the same time, we know that this change is zero. And if we know that, that was Siri. If we know that, we can do the following. We can integrate all over the location. We can integrate from 0 to Lg. We can integrate from 0 to Lg and say that this is constant. And if this is constant, we get current times Lg. So the left side, if we do the full integration, you get Lg times Id. Now let's concentrate to the right-hand side. From which value to which value we have to integrate the voltage? We have to integrate it from 0 to VDS. This is equivalent. From 0 to LG, it is equivalent from 0 volt to VDS. This equivalency is now here on this slide. So again, repeating, the left side I have just copied, and the right side of the previous equation, is here. And now we integrate from 0 to VDS. And we know that this result is this one. We know that. Okay. Okay, let's put LG to the left-hand side. What is constant? So let's mark all the constants. This is constant, this is constant. LG is constant, and ID, the drain current we have here. So the rest is this one. And if we put in the QX equation, we put it in here, we get this. Okay, let's concentrate on the integration of this equation. There we get some constants. What we do get, if we integrate a constant as a function of the voltage, we get the constant and the voltage. Okay, I mark them with a different color this time, and this value we get here after the integration. Minus, we integrate Vx, and we know that Vx is a constant, has a constant slope. And if Vx has a constant slope, the integral is 1/2 to the square of this end of your integration. Okay, so we integrated this one also with very easy assumptions. What is left? This bulky guy. And this bulky guy, this one, is this small equation, you know? Okay, so we put in this small equation and we integrate this small equation from 0 to VDS, and we get the result. And the result is the drain current is a function of all that stuff. Let's analyze the equation. This is the so-called transconductance parameter. What does that mean? The main function of a transistor is its Steilheit, transconductivity. That means you change the control voltage, gate source, you get a changed drain current. So voltage to current translation. That's the main function of a transistor. Gate source voltage to drain current. And this parameter defines your drain current by physical values, by the gate length, by the gate width, by the mobility, and the oxide capacitance. So let's take a closer look to this transconductance parameter. If you make your oxide thinner, then the capacitance increases and your current increases. If you make your transistor wider, then you can understand it by looking at it. The motorway is getting wider, you have more current, for sure. And if you change the length that the electrons have to travel and make it shorter, then the current increases also. And the only parameter you are able as a designer for integrated circuits to manipulate is this pair. This is the only pair of values you can manipulate, the width and the length. The rest is defined. Okay, now let's go towards the rest of the stuff. So what is our aim? Our aim is to find out the drain current as a function of VGS, we have it here, and VDS, we have it here and here. So that was our aim. And we find out that if you increase the gate voltage, you increase the current. Yeah, but if you increase the drain source voltage, you reduce the current. And there is also some doping dependency because the Fermi level, referred to the intrinsic level, is a function of the doping level. That means you can now change all this stuff by designing the required um, drain current by manipulating the doping level, by changing the oxide thickness. Oh, one moment, please. It's not so easy, like I have said, changing the oxide thickness. You have a changed drain current. The oxide thickness change is here in the denominator. uh, Therefore, I have put these dependencies into a question later here. Uh, okay, very much later. Sorry about that. It is here. We have some dependencies of the oxide thickness. Do you find it? Here. Concentration. No, no, doesn't mind. I have some questions where you have to use the Excel sheet I have provided you to understand the dependencies of the oxide capacitance, the doping level, and so on. Okay, so play around with the spreadsheet. You get a certain drain current as a function of your variables. So this is given by physics. And if you want to simplify that stuff, you can say it looks like this. And do you see what we have here? We have here increased drain current with the drain source voltage and proportional to the square of the value, you have a minus sign. So this is something like this, okay? Your paraboloid trace of a ball thrown into the space. And the validity, so the voltage area where this is valid, this equation, is for VDS is smaller than V overdrive. That means this equation is only valid, the simplified equation is only valid towards this tip of this paraboloid. Okay, that's German. 1 second. I have to cut that area in pieces. So in this area, this equation is no more valid. Therefore, more physical um, simulation models take into account all parameters, and more simplistic equations just take into account this way of calculation. Okay, so we keep on using, guess what? This equation, the more simplistic one. Well, I have just copied this equation to here. Now let's take a look onto the characteristic curves of a transistor and break down the parameters to their values. Okay, so the beta is here the transconductance parameter. Uh, the bipolar transistor we haven't learned yet, right? Okay, so this beta will have for the bipolar transistor a different meaning. Okay, V to L relation is proportional to the transconductance parameter, vice versa. So if we take the width to the length a factor of 1, so let's say 5 micrometer length, 5 micrometer width, then we have 1. Then we have, let's take a look to other values, the oxide thickness, it is here. So the oxide thickness normalized to the area is epsilon to the oxide thickness itself. The oxide capacitance is then the result of epsilon 0, epsilon r. Epsilon r is the one of the silicon oxide, so it is roughly 3.9. And the typical thickness is 7 nanometers. So you get an oxide capacitance of roughly 5 femtofarad per square micrometer. So now you know by heart what the capacitance you get after your design is finished. Mr. Botta, that's important for you. So you said we can use this oxide as a capacitor. Yes, we can. Let's assume you draw a transistor with a width and a length of 5 micrometer to 5 micrometer. We have an area of 25 micrometers square. And this transistor has an oxide capacitance of 5 times 25. That means, oh, please calculate. No, 10 times would be 250. It would have then 125 femtofarad. Is it true? So no, that's false. 10 times would be 250. What we have in 10, we have 25. Oh, that's far larger. Okay, sorry about the bullshit. Uh, how much again? How much? What is the value again? 120. Okay, 125 picofarad. So this small area generates 125 picofarad. That's a large value for signals. Let's calculate at 1 gigahertz the impedance of this capacitor. Okay? So the impedance of the capacitor, so uh, der Betrag, These are basics, but I have missed the word. Leo.org. The absolute value. I I know the absolute value. The ma yeah, the magnitude. So the magnitude of this of the impedance. So it is calculated by 2 pi f times uh, capacitance, C. So what do we have as an impedance? So the absolute value of the impedance. Yes, please. Okay, so it looks like this. If you have 5 times 5, you have 25 square micrometer. So you have to calculate 5 times 25. So 5 times 25 is 125. You're right, femtofarad. Yeah. Sorry about that. Okay. Yeah, 125 femtofarad. That's not so much, but also useful value. 1 divided by 2 times 3.14 times 1 gig times 125 millimicro nano pico femto. That's 1000, 1 dot, let's say 3 kilo ohm. Okay, so the impedance level is 1.3 kilo ohm. By having so small area, and if you go towards high frequency applications, you go towards impedances which is in the center of the Smith chart. And the center of the Smith chart is usually normalized to 50 ohm. That means all impedances are in the surrounding. So left side is towards 0, so that's 10 ohms, and right side is towards kilo ohm, so 100 ohms, something like that. So this is the area where you are if you do analog design. Just take reference all these values to real impedances at the frequency of interest. Okay. Um, the second thing, now Cox we have. We go on and take a look at the mobility. And with the mobility, we assume, as a rule of the thumb, it is 600 for the electrons. But you have the EOFL page on my spreadsheet that the mobility is a function of temperature, it's a function of the doping level, and so on. But well, you assume it's 600. And at the same time, the mobility for the holes is less than the half of this value. Why? Because of the EK diagram. Yeah, the energy momentum diagram. The holes have less bending than the electrons. And if you have less bending, the bending is inverse proportional to the mass, effective mass. That means if your holes have less bending in the a key diagram, then your mass is higher, the effective mass is higher. Therefore, you say it here, well, okay, 600 for the electrons, 250 for the holes. Now you get, if you put in the oxide, the mobility in, you get this value. And this value says, that's interesting, you get 290 microamp per square volt. Let's take a look to the equation, Y square volt. Here you have your overdrive voltage times VDS minus half VDS square. And let's take a look. This is VDS and this is ID. If we take a look to this equation, which is valid to this tipping point, VDS is equal to V. What is this limit? What is the name of this limit of the VDS? V index. Yeah, and what is the value, relative variable value? No, it has something to do with the threshold voltage. That's the very important point. Therefore, I haven't given you the answer. This is exactly this one, where your channel, starts to pinch. And if the channel pinches, and this happens if VDS is equal to V overdrive, you are exactly at this tipping point. Okay, so we have now the link to of these slides. Therefore, I'm asking all these questions where I give the answers. Okay, that's V overdrive. Now, if you put in this equality to here and here, you get the ED max is equal to beta times 1/2 V overdrive square. Why? Because this is V overdrive and VDS is V overdrive and VDS is V overdrive and V overdrive square minus 1/2 of V overdrive is 1/2 of V overdrive square. Yeah, that's it. That means your maximum current is defined by you and by you, by your design of your transistor. So if you want to have a smaller transistor, then you have to supply more overdrive. But your overdrive is limited to a value where the oxide breaks down. So your current is limited by the voltage you can drive over and by the physics of the limits of your area. Okay, so that's the point where we are to understand the MOSFET. So putting all this information vice versa towards questions, I can ask you how you can increase the current of the transistor if you are a technician. Okay, if you're a technician, you can say, I try to increase the mobility. How you can do this? You can make the surface smoother. Great. Between the silicon and the oxide. Then you can also change the oxide thickness. Then you can change the beta. And you can increase the width and reduce the length. And then I can say, one moment, please. If you reduce the length, what is the limit? The limit is where this length is the minimum value your lithography, your technical equipment can make this, yeah, etching processes. So as small you can make that stuff, as high you can get the current, or as low you can further reduce the width for a certain amount of current. Okay, so this is all the stuff the industry is working at, reducing the oxide thicknesses, reducing the minimum length in order to make transistors which are smaller and smaller for the same current. Okay, so here we are. So this line is exactly what we say. Now our overdrive is 1 V threshold. Why? Because our gate source voltage is 2 V threshold. And the V overdrive is VGS minus V threshold. And if your VGS is 2 threshold minus 1 threshold is 1 threshold. So don't be disturbed from this index. It is the overdrive voltage. It is one less threshold than the gate voltage. Okay. Um, so I have put this equation into Excel and have plotted it up to here. Then I have drawn a dashed line. So this diagram is generated this way around. So go on and take. So I have to remember, to memorize where we are. I have at the left top corner the area where we are looking at. And in this area, now we look at this graphs. And what do you see at a glance? It is linear. Why it's linear? For sure, if you take this equation and make this value small, and you square this small value, then it gets smaller. And smaller value, which is taken minus, I neglect. And say the rest is remaining for very small drain source voltages. And this part I have copied to here. And now you see the drain current is proportional to the drain source voltage. And what is VDS divided by ID? It is the resistance. So the channel resistance in power electronics is exactly this. That means if you want a transistor with a certain channel resistance, you have to increase what is inside of beta V divided by L. You have to increase the width and minimize the length. And any power transistor, take a look at CoolMOS from Infineon. That's one very popular super junction MOSFET for high voltage applications. These super junction MOSFETs from Infineon, if you increase the gate voltage, you reduce the RDS, the drain source channel resistance. And if you plot this here, you get all these equations. And the task is now to just calculate these resistances with these bias voltages and give me the result, please. So for all these calculations, this equation is valid. And for beta, please take this value and this value. Oh, no, just this value, because this is inside beta. Sorry. Okay, so 290 microamp per square volt. We go there and put it in here. Beta is 290 watt per square volt. But microamp, I think. Okay. So the important point is it's 3 times because it's the over voltage, not 4 times. The over voltage is 1 VTH less. What is the result? I have an error here. My 1456, 30, 37. Okay, great. I think the units are here misplaced. 1 second. This ampere keeps to be at the denominator. Now it's correct. Now we have the square. Yeah. And for this one, we need to calculate RDS3 times 3 divided by 2. Yeah, because we have to exchange this 3 by this 2, because this 2 is 3 minus 1. Okay. It's Dreisatz. It is if you want to take this one, you have to X out this 3 by multiplying it, and then you replace it by 2. Okay. Okay, that's a good value. 2.2 kilo ohm. So it is 1.4 kilo ohm. And here at the lower end, 4.3 kilo ohm. So that looks good. for on my side. And that means you have an ohmic resistor for low VDS, but you already start to see that it is not really ohmic. It starts to stop, increase somewhere, the current. Okay, now we have this ohmic region. This ohmic region is used not only in power electronics to switch on and off the transistors, but also for, let's say, switched capacitor applications. What is that? Switched capacitor. Oh, I need a coffee. What is stored in the capacitance? Charge. So if you assume this is charge, and you take this charge and pour it off, so the charge is moving. So you can charge up the capacitor and discharge it. Then you have a portion of charge on the way. And if you do this very often, very fast, faster than you can see, then you can assume this flow is not quantified, it is static. That means you can set the current level by switching the capacitor with a certain frequency. And this is done in integrated circuits to control the current level as a function of the voltage, because capacitor, voltage, you charge it up, and with a certain frequency, you pour it out by switching, switched capacitor. And this means you have a voltage, you have a current. What do you have? A resistance. You can set virtually the resistance of a circuit by changing its frequency. And you can set these virtual resistors to very large resistance values. But why you do that stuff with transistors and capacitors and switching it? Because they are so small. Let's say 1 mega ohm as a resistor is that large. 1 mega ohm as a switched capacitor is that small. So all the matter is the cost of that stuff. And it is adjustable by the frequency. You pour out that stuff. You would learn that in the master course. That's now Dauerwerbesendung. That's now an advertisement channel here now for our master. Ah, no, you have to learn German. Yeah, damn, I know. But it's very interesting, you know? It's worth to do it. Okay. Well, let's go on with our stuff and set it to a certain point. We have learned the linear region, what is valid there. Then we go to the point where we are at the pinch-off. This pinch-off voltage occurs in our simplistic way of thinking if we apply just V overdrive. In reality, you apply this voltage. Now you can compare using my spreadsheet what the difference is in the value. And therefore I say the real value is calculated this way, and the approximate value is your overdrive voltage. Okay, so this is all what I wanted to say for the pinch-off, because we know this point already. Now we go on and take a look at here and at the maximum current. Now we get it here again. We have 1/2 beta times the 1 for the overdrive square. That's the maximum point. If you plot these maximum points as a function of the gate source voltage, you get this very important transfer characteristics. The transfer characteristics, you can print it out and say that's the function why we do a transistor. The gate source voltage, you control it. And by putting this control, you get this current. That's the response of the transistor. And this response is taken out from the transfer characteristics. And for the MOSFET, this current starts at the threshold voltage, and then it increases as a function of the square, by the square of the overdrive voltage. Now I have it here. Um, and a square function looks like this. And now remember, we have also bipolar junction transistors. And bipolar junction transistors have exponential current characteristics. And this is not a joke. This is just a plot of the equation of a bipolar transistor. Now you see the disadvantage of the MOSFET. Up to now, we talked about the advantages. Now you see the disadvantage. The disadvantage is in the main function of the transistor itself. The transfer function has a certain slope. So you have a signal in the x direction, that's the voltage gate source, and this signal produces a current through the transistor. So this capability to transfer a gate source signal to a drain source voltage current is limited, and this is the slope. And the equivalent transistor as a bipolar transistor, you can't see in this scale the slope. That means the bipolar transistor is far ahead of any MOSFET if it comes to signals. But the CMOS, the complementary MOS, PMOS and NMOS is the CMOS. This complementary MOS, the CMOS technology is far ahead of the bipolar because it has both types of transistors. So you can't have both advantages in one device. That's what I wanted to tell you here. So you can use a PMOS as a source of current. You can use an NMOS as a sink of a current. What is the characteristic curve of a current source? It is just a line. And if you compare this characteristic curve of a constant current source to the transistor, yes, it has also a constant line, but down to the overdrive voltage. That means if you keep in this area, your transistor is a so-called current source or a current sink. Yes, Mr. Botta. Your voice was partly transmitted to me. Mhm. Okay. Square root to the overdrive voltage. Yes. Ah, yes. That's seen here in these distances. So you increase the threshold, you increase the gate source voltage. So linearly 0, 1, 2, 3, and so on. And the distance is increasing further. Great. Not at all. um, perhaps. One moment. Perhaps you can map this. One moment. I have an idea. I have answered your question, but nonetheless, I have an idea. Perhaps you have here this current for 2 VTH, for 3 VTH, you have this current, and for 4 VTH, you have this current. Yeah, okay? Not at all. Good. Now we have these output characteristics in the first approximation as a constant current sink or a constant current source. And for the sake of simplicity, you say for a transistor, if the gate source voltage is constant, it is a current source. Although the NMOS sinks a current, you say that this transistor is a current source. Don't be disturbed from this discrepancy. So the transistors are, in the first approximation, all current sources, although they are pulling the current towards the ground. Uh, I think if we want to take a look to the channel modulation, it's too much for today. The weather is nice. We are very tired. The coffee is almost empty. I would say, yeah. I know. I can hear you. I would like you to take a look on this for the next lecture next week. Then we can understand this slope a little bit more, and then I will tell more than this guy is telling you. Okay? So for today, it's enough that, and I wish you a very pleasant week. See you. You too. Bye bye. Thank you, Mrs. Akbar, Mr. Sulak, Fernando, Rausha, Sönmez 9, Mukha. Bye bye.